Hi, George Diamond here again. Now today we're here to finish up our look at section 7.2. Today we're looking at volume by the disk and washer method. Now my first video, we looked at calculating the volume of a region that had been revolved around an axis of revolution, basically using the disk method. Now today we're going to take a look at something very similar, right? But this is called the washer method. So the two techniques are pretty much the same. Except, with the washer method, a washer, remember, is a disc that has a hole in the center. All right, so it has a hole in the center. So these problems are, typically a little bit more difficult than just a disc problem where you're revolving a region around a particular line. So the x-axis, y-axis, or some other line. So these are a little bit more involved, in which you got to be more careful about describing your radiuses, if you will. Now, whenever you look at a washer, remember a washer is simply a disc with a hole in the center. So you've got the what we call big R. Now, big R is going to be the radius from the center of the circle to the outside function, right? To the outside function. Little r is going to be the inside radius. So you have what's called the outer radius and the inner radius. So the outer radius would be the radius from the center, or in our case, when we set our problems up, it'll be from the line of rotation, or from the axis of rotation to the I guess the graph that's furthest away from your axis of rotation. And then you have little r. Little r is going to be the radius of the inside function. That is, it's going to be the radius, or the distance from the axis of rotation, or the line of rotation, to the function closest to the axis of rotation. Now, when we calculate the volume of a washer, the volume of a washer will be pi times the radius squared. Okay, that is the area of the inside region, if you will. Okay, minus the area of the outside region, rather, with big R, so pi times the radius squared. Okay, minus the area of the inside region, so pi times little r squared. So the area of the outside region minus the area of the inside region times the thickness of the washer gives you the volume of a washer. And we can kind of simplify this expression when it comes to calculus now. Pi times big R squared minus little r squared. Big R is going to be the outside radius, little r is the inside radius, times dx. Dx represents the thickness, if you will. And you write this as an integral. Right? So if you look at my region and my little graph here, you can imagine this little region right here is the intersection of two curves. Okay, here we have our representative rectangle. Now, if you were revolving this about the x-axis, big R would be this distance here, from the top of your representative rectangle to the x-axis. Little r would be this distance from here to here. It is from the bottom of the rectangle to the x-axis. Right? So when you set this up in calculus now, okay, our volume is going to equal pi integral from a to b. Right? So if you're revolving about the x-axis, right? From a to b, big R squared minus little r squared times dx. Now if you're revolving about the y-axis, or yet another vertical line, then instead of dx, you're going to have to solve for y, and that would be in terms of dy. And we're going to do a problem where you have to revolve a region about the y-axis and the x-axis. We'll do one of each. So we've got 3 examples, right? And let's take a look at our first example now. So take a look at the first one. Erase this. All right. And like I said, now using the washer method. The washer method is a little bit more challenging for a lot of students, because you really have to be careful as you describe the big R and little r, the outside radius and the inside radius. Now let's take a look at problem number 1. Let's start off with a fairly simple problem here. So number 1 says find the volume of the solid formed by revolving the region bounded by the graphs of y equals the square root of x and y equals x squared about the x-axis. So if you look at the graph, I put a little graph here on my problem. You can kind of see it, get an idea of what the graph will look like. And let me see if I can sketch this. Well, as you look at it, we got something like this. And we'll sketch the graph. I may have to take this problem off my marker board. So if you're taking notes, you want to go ahead and write that problem down now, because I may have to take this down in just a minute if I need some extra space to work my problem here. So as you look at your graph, you've got so you got this is y equals x squared. And we got the square root of x, which if you remember does something like this, it does something like that. This is y equals the square root of x. And you can see you have two intersecting lines. You have this region in the first quadrant. Now we're going to see if we can take this region right here, and we're going to revolve that region about the x-axis. So we take this region, we're going to bound it about the x-axis. Let me draw a representative rectangle. A representative rectangle will look like this. So what we get when we revolve this about the x-axis, we're going to get what looks like a bowl, really. So it kind of looks like a bowl, I guess. All right, so to get started now, a couple things we need to do first. Let's get our intersection points, because we need to see what the bounds, the upper and lower bound for integration will be. So the upper and lower bounds would be from here to here. So it looks like one of them is going to be at 0. But let's start off. Let's see if we can get our points of intersection. Now to get the intersection points. So to get our intersection points. Okay, we've got to set the two equations equal to each other. So we've got x squared equals the square root of x. And then we have to solve this for x. So let's take the square this side, we'll square this side here, gives x to the 4th equals x. Let's move the x over, gives us x to the 4th minus x equals 0. Right? So to solve a quadratic, or not a quadratic equation, but a little polynomial function like this, little polynomial equation. Let's get 0 on one side. Now we've got to factor this. Factor x off, gives x times x to the 3rd power minus 1 equals 0. And x to the 3rd minus 1, this is a cubic binomial. As you factor this, now this would factor as x times x minus 1 times x squared plus 1x plus 1 equals 0. Now the trinomial here won't factor again, so you end up with x equal 1 and x equals 0. Right, so our intersection is going to intersect from here, from 0 to 1. All right, so from 0 to 1. That's how we get our intersection. So to get your intersection, like I said, you have to set basically if you're both solved for y like this, you're using the substitution method, set the two equal to each other, then you have to solve for x. Right, now if we need the y values, then we can substitute back in to get y. But let's see, as we get started, now let's describe a big R and a little r. Right, now big R, okay, big R, the outer radius. So remember, when we set up our volume is going to equal pi integral, in this case from 0 to 1, okay, big R squared minus little r squared dx. All right, so we set up our integral, we'll set it up like so. Now, big R would be the outer radius here. So the outer radius, that is the radius, the graph that's furthest away from your axis of revolution. Now, axis of revolution is the x-axis. Remember, we're going to rotate this about the x-axis. So the outer radius would be this right here. Right, so that's going to be big R. Now that distance is that's our top function, which is the square root of x. Right now, little r would be this distance right here, which would be x squared. Right, so this would be the square root of x. Little r would be x squared. So as we set up our integral now, okay, our volume will be equal to pi integral 0 to 1. Big R we said is the square root of x, so it'll be the square root of x squared, okay, minus x squared dx. Right. Now, we'll do 3 problems. The first 2 problems, I'm going to work everything completely out. Right? So we'll get our answer. I'll show you step by step how to work it out. Now, the last problem is going to be like a 4-part problem. We're just going to set the problem up. I'm not going to work them all the way out, just to kind of condense the video a little bit so it won't be quite so long. I'm assuming that by now, we should be able to find an antiderivative and evaluate a definite integral. All right? So I'm assuming that's going to be the case. Now, to simplify this, let's see what we get. Now, also, make sure you remember, okay, this is pi times your integral, big R squared minus little r squared. Don't forget the pi. Now, I like to put the pi on the outside of the integral, but But you got to bring it down each step, and remember that pi is still there. So at the end of your problem, you got to remember to multiply by pi, all right? So as we evaluate this, I want to simplify this a little bit. This will be pi integral 0 to 1. The square root of x squared is just x minus, this will be x to the 4th dx. Now it's a matter of getting our antiderivatives here. This will be pi times, this will be x squared over 2 minus x to the 5th over 5 from 0 to 1. Okay, now we want to substitute the upper bound minus the lower bound, and let's see what we get here. This will be pi times, so pi, I'm going to use different grouping symbols. This will be 1/2 times 1 squared minus 1/5 times 1 to the 5th power minus, substituting 0 in gives us 0. All right, and we have pi times, this will be 1/2 minus 1/5. So 1/2 minus 1/5, which is, let me come over here, equivalent to pi times, denominator of 10 here. All right, so first it'll be 5/10, and so 10, and this will be 2/5, or 2/10. Okay, combining this will give us pi times 3 over 10, or 3 pi over 10. So our volume here should be 3 pi over 10. So a fairly simple, straightforward problem. So if you were to rotate this shape about the x-axis, you would get, something like this. It would look like this, rotated like so. So you get some type of would look like a bowl shape, I guess. So kind of a bowl shape. All right, so this is our first example. On to example number 2. So problem number 2. All right, now this is kind of the low-tech version of a screen within a screen, I guess. So it kind of works for me pretty well. So hopefully you can read these all right. But erase this. Okay, now problem number 2. Now problem number 2 says, okay, find the region, what's the volume of a region bounded by the graphs of y equals x squared and y equals 2x, and it was revolved about the y-axis. So it was revolved about the y-axis. UT, there you go. So the y-axis. Let's try revolving this about the y-axis now. So let's see now about the y-axis. So as you take a look at this problem here, so let's see, we've got a linear function y equals 2x. Let's see if I can sketch this up here again. All right, so you've got okay, y equals x squared. We'll do sort of like this, I guess. Okay, y equals 2x will be the linear function. It's going to do like so. So y equals 2x, and the bottom function here will be y equals x squared. So we'll write that down. Okay. Okay, there we go. All right. We're going to revolve this region about the y-axis. All right, so about our y-axis. Now, if we set this up, and go ahead and draw our representative rectangle. Representative rectangle. Remember, your representative rectangle is always drawn. You always draw it perpendicular to your axis of rotation. So if you're rotating about the x-axis here, this should be perpendicular to the y-axis. If you're rotating about the x-axis, it would have to be vertical. So you draw a representative rectangle. All right. Now, we're revolving this about the y-axis. All right. So this time, the distance from the y-axis to the red function, that is the curve, okay, that's going to be our outside function. The straight line would be our inside function. All right. So as you set this up, you want to kind of keep that in mind. So big R would be the distance from the y-axis to the curve. Little r would be the distance from the y-axis to the straight line. So as we set this up, then let's see if we can describe. Well, first let's get our intersection. Also, we have to solve these for y. So we're revolving about the y-axis. So our equation here, this is y equals x squared, I guess. change that, so y equals x squared. Now, let's see if we can solve both of these for y. All right, so solve for x. We'll just solve for x in terms of y, so we have y equals to x, and we 1/2 y equals x. And the other one, we have y equals x squared, so it'll be the square root of y equals x. So let's solve each one of those for x in terms of y. So we've got to do that. Okay, and also I need to get my my upper and lower bound here. Now to get the upper and lower bound, let's see if we can solve this for y. So let's get our intersection. All right, so let's get our intersection. This will be in terms of y. So let's take, let's see. Let's take the 1/2 y. Set that equal to the square root of y. Let's square this side, square this side here. That gives us 1/4 y equals, that equals y. Let's bring the y over. This will be y squared, so 1/4 y squared equals y. This becomes 1/4 y squared minus y equals 0. Let's factor the y off, and we have y times 1/4 y minus 1 equals 0. Now solving this for y, we have y equals 0, and 1/4 y minus 1 equals 0. Okay, 1/4 y equals 1, or y equals 4. So we're going to multiply 4 to both sides there. So we have y equals 4. So when you look at our upper and lower bounds now, we'll go from 0 up to 4. All right, so from 0 to 4. Okay, that'll be the y values of our intersection points. Okay, so we got our intersection. That wasn't too bad. Let's set up let's see if we can describe big R and little r now. So let's see if we can describe each of those. Now, big R would be, let's see, we'll describe big R would be this distance, if you will, from here to here. All right, that's the point, in this case would be, see, that's the curve here, so that would be the square root of y. And the little r would be here to here. So big R would be the square root of y. Little r would be, from this distance here would be 1/2 y. Right, so this would be 1/2 y. Right. So as we set our integral up now, our integral will be v equals pi, integral from 0 to 4. Right, so we got our upper and lower bounds now, from 0 to 4. So big R we said is the square root of y, so we'll set this up. The square root of y squared minus, so minus 1/2 y squared. Okay, dy. Let's see if I can erase this here. Gonna get it away. There we go. All right, and now let's see if we can simplify our integral a little bit. This becomes pi integral 0 to 4. Let's see, as you square it becomes y minus 1/4 y squared dy. Right. And once again, with this example, I'm going to work this example all the way out to get the final answer. Right? So we're going to work this one all the way down. The next example, I'm not going to. So these first two, I'm going to work them all the way out. So let's start off. We've got our integral simplified. Let's find our antiderivative now. So it becomes pi, which from this will be y squared over 2 minus, becomes 1/4 times y cubed over 3. Okay, from 0 to 4. Okay. Now let me simplify this a little bit. So it'll be pi times 1/2 y squared minus 1/12 y cubed from 0 to 4. And so I'll simplify it just a little bit. Now let's substitute the upper bound minus the lower bound, and it should give us our volume, right? Just once again, make sure whenever you set your integral up, remember now, we're revolving this about the y-axis, right? So you got to remember to put that pi on your integral, right? A lot of teachers teach put the pi inside the integral, okay, with the function, but it kind of gets in the way a little bit. It's not like you pull it out. You just have to remember to bring that pi down each step, right? Because if you leave it out at the end, you know you're going to be off. So let's substitute the upper bound minus the lower bound. This will be pi times Substituting the 4 in becomes 1/2 times 4 squared minus 1/12 times 4 cubed. Okay, minus, substituting 0 in for y, so it will be 0. Okay, and let's see what we get as we simplify this now. This will be 4 squared is 16, half of 16 is 8. This is pi times 8 minus. Now 4 cubed is 64. This will be 64 over 12. All right, so it'll be pi times 8 minus 64 over 12. And let's see, 64 over 12 will reduce to 16 over 3. So this becomes pi times 8 minus. So 8 minus, this will be 16 over 3, right? So here we go. So 16 over 3, and let me erase this. Okay, we're almost done. We just have to do the arithmetic here to finish this up. So this will be pi times 3 minus 16 over 3. And in the denominator 3, so this becomes 24 over 3. 24 minus 16 gives us 8 over 3, so this will be 8 pi over 3 for our volume. So example number 2, that's how you do it. Right? So you got your, so the red function was big R, so that gives us the radius of the outside function. The inside function is the linear function there, and that's how you want to set it up. So you got big R squared minus little r squared. And like I said, you can't actually do this as 2 separate integrals. Right? So a lot of teachers actually teach to do these types of problems. They actually teach to do this right here. And set this up as pi integral 0 to 4 square root of y squared dy minus pi integral 0 to 4 1/2 y squared dy. So a lot of teachers teach this right here, to do 2 separate integrals, right? So it does kind of hold them a little bit on the confusion a little bit. But a lot of times, you can simplify when you combine them as one integral and you're integrating. A lot of times you can simplify them quite a bit. But either way will work. But you can, like I said, you can do this as 2 separate integrals. With one integral with big R, and one integral with little r, and then just subtract the 2. Okay, now let's try example number 3. So example number 3. Okay. Let me get this one out of the way. All right, now this next problem is a little bit different. Remember I said the first 2 problems we're going to work out completely. Also, I've been doing a little cleaning here, getting some formula 409. Let me see if I can move this out of the way. Okay, I like being tidy and clean. There we go. So let me move this out of the way. So let's take a look at example number 3. Now with this here is actually, it's one problem, but it's 4 parts. And I just got this is a problem out of our textbook. It's one of our homework problems. So we're going to do something like it, right? Because my students, they're going to be faced with, after they watch this video, they're going to have to do a bunch of homework on this. And they're going to see this type of problem. It says, find the volume of the solid form when the graphs of y equals 2x squared, y equals 0, and x equal 2 is revolved about, first, the y-axis, then the x-axis. Okay, what if we revolve it about the line y equals 8? So we're going to try revolving about a line that is not an x-axis or a y-axis. Okay, and the line x equal 2. All right, so if you look at this region now, I've already kind of described it. You got y equals 2x squared, that's your parabola. We've got the line x equal 2, so this is simply a vertical line, so x equal 2. So let me see if I can sketch this over here so I can draw on a little bit. All right, so this needs to be 2 here. And let's see, we've got our vertical line. That's x equal 2. We got our parabola. And our parabola is going to do something like this. Sort of like that. So let's see now. Typically, if to get your intersection point, you would set 2 of your functions equal to each other. So we're trying to find the intersection of the vertical line and the parabola here, but now this is simply x equal 2. So really to get my y value, all I need to do here is substitute 2 in for x. All right, so to get y, it will be y equals 2 times 2 squared So it'd be 4 times 2 would be 8, so it'd be y is 8, so you talk about 0.28. So this point right here is the 0.28, and the y value here is 8. All right, so if I have to revolve about the y-axis, that's going to become important now. Okay, so let's start off. Let's see what we're going to do. Let's do part A first. We're going to see if we can revolve this about the y-axis. All right, so A. So the y-axis. Now, keep in mind, I'm not going to work this problem all the way out. We're just going to set it up. All right, so to kind of save a little bit of time, so all we're going to do is set the problem up. All right, and so let's start off. Let me sketch my, and revolving this about the y-axis. Let me sketch our representative rectangle in here. Okay. All right, let's see if we can describe big R and little r. All right, now big R first. Now revolving this about the y-axis. So once again, the y-axis is our axis of rotation, and so the outside radius here would be this distance right here. So that's going to be big R. Right, so big R is going to be 2. Okay, now little r. Okay, now little r, the inside radius would be this distance right here. Okay, that would be this distance right here. Okay, which would be, let's see now, we're doing this with respect to, we're revolving this about the y-axis. So I forgot to do this, but I need to do this now. I need to solve this equation here for y. Yeah, so we need to do that, or for x in terms of y. So solve for x. For x. All right, so since we're revolving this about the y-axis, now we got y equals 2x squared. That gives us 1/2 y equals x squared. So the square root of 1/2 y equals x. Now it can be plus or minus, but we don't need the minus. All we need is the positive value, so it'll be the positive half, the negative half will be the other side. So this will be the positive square root of 1/2 y. Right, so this distance right here would be 1/2, so the square root of 1/2 y. So the square root of 1/2 y. So that would be that distance there. So little r. Now, so to describe this distance right here, now this is the distance that I need to describe. Now, so that would be the length on our representative rectangle. So from here to here is 2, right? So from here to here is 2. Okay, that means that this distance right here would be, okay, would be 2 minus the square root of 1/2 y. So little r is going to be 2 minus the square root of 1/2 y. So that will be little r. Well, actually, no, it won't. Let me just change this a little bit. It will not be. So our outside radius would simply be 1/2 y. 1/2 square root of 1/2 y. So little r would simply be the square root of 1/2 y. Would be this distance right here. So it would be the distance from this end of the representative rectangle to your axis of rotation. In this case, would simply be 1/2 y. So we set up our integral now. Our volume becomes pi integral. Now this time we're revolving this about the y-axis. Will be our lower bound will be 0. Our upper bound will be 8. Okay. Big R squared minus little r squared would be 2 squared minus the square root of 1/2 y quantity squared. Okay, dy. Erase that. Big R we said is 2. Okay, this will be our integral. Now I'm going to take it one step and see if we can simplify this a little bit. So it becomes 0 to 8. And this will be 4 minus 1/2. So 1/2 y. Okay, dy. And from here it's just a matter of finding your antiderivative. And like I said, I'm not going to work this one all the way out. We just want to set it up. Right. Now, same problem. Now this time to do part B, let's see if we can rotate this time about the x-axis. Let's do part B. We revolve this about the x-axis. All right, so about the x-axis. All right, so this time, as you look at our graph, let me erase this. Let me draw my graph back up here again. All right, so we've got like so. Okay, this is x equal 2. Okay. And then we set our parabola goes up like so. This is the point 2, 8, and the y value out here is 8. Right.
Now, this time revolving this about the y-axis, this is simply the disk method, all right? So the disk method, this is really not a washer. So you can see it's bounded by the x-axis here. So you take this region, you revolve it about the x-axis here. You know, big R, we do have I guess big R, little r here would be 0, looks like. So as we set this up, let's describe big R and little r. So big R would be, drawing our representative rectangle now would be like so. Right, so our representative rectangle. See how big R would be this distance right here, this height. Okay, that's going to be big R, which would be your function. That would be 2x squared. All right, so it would be 2x squared would be big R. Now little r would be the distance from the x-axis to the bottom of that rectangle, which is 0. So little r is 0. So we just have the big R here. So if we set up our integral now, our volume would be pi integral from 0 to 2, right, so 0 to 2. We're revolving this about the x-axis now, right, so the x-axis this time must be 0 to 2. 2, right, so 0 to 2 for our upper bound and our lower bound. And this would be 2x squared dx. So we set our integral up, this is what our integral will look like now, right? So to simplify a little bit, it'll just be pi integral 0 to 2, which is 4x to the 4th dx. And then from there, it's a simple matter of getting our antiderivative, substituting the upper bound minus the lower bound. Okay, let's take a look at part C. Now part C, it says take this region and revolve it about the line y equals 8. So the line y equals 8. All right, so part C. Okay, the line y equals 8. All right, so the line y equals 8. So let me erase this. Erase this here. Here we go. Okay, make sure this is correct. So y equals 8. Okay. Now let's see. Now the line y equals 8. So y equals 8 is simply a horizontal line, like so. So that's going to be the line y equals 8. It's going to be that line. So this time we're going to take this region and we're going to rotate it about that line. Now this time we're revolving about a line that is not the x-axis, or a different line this time. As we draw our representative rectangle, it would look like so. Put a representative rectangle back in. Now first of all, big R. Now for big R, we're talking about the distance from the axis of rotation to this line right here. So this right here would be big R. All right, so this case would be 8. So as we describe big R is 8. All right, so big R would be 8. Okay. Now I know that this distance right here would be 2x squared. All right, so what I need is this distance right here, from here to here. So if we can describe that distance there, okay, that's going to be our inside radius. So that would be the distance from the axis of rotation now to the top of that rectangle. All right, so top of that rectangle. Now, I know that the rectangle itself here would be from this distance here would be 2x squared. So the rest of this distance from here to here would be 8 minus 2x squared. Right? So little r would be 8 minus 2x squared. So big R is going to be 8. Right? So that's the distance now from the axis of rotation, from the line y equals 8 to the x-axis. Okay, that would be to the bottom of your representative rectangle. Little r would be the distance from the axis of rotation to the closest end of the representative rectangle, right? And so this distance here would be 8 minus 2x squared. So we set up our volume expression now. Our volume is going to be pi integral. Now we're rotating this about a horizontal line, so still with respect to x here, I guess, 0 to 2. So 0 and 2 will still be our upper and lower bounds here. So 0 to 2. Now big R would be 8 squared minus, this would be 8 minus 2x squared dx. And then evaluating this should give us our volume. Now I'm not going to do the entire problem. Like I said, we're just setting the problems up
with problem number 3 here. Okay, let's do one last part here. Okay, one last part. Erase this. And there we go. Now, what about reflecting our graph, our region, if you will, across the line x equal 2? So let me make a sketch this over again. That's x equal 2, all right, so that's the line x equal 2. And we've got our parabola. That's 2, 8. 8, 0. All right. You know, this time we're talking about taking this region and instead of revolving it about the y-axis, okay, we're going to revolve it about this right-hand side here. Now you notice how the region actually butts right up against, or it's right adjacent to, or next to the axis of rotation here. So this here is going to be our axis of rotation here. So that's the line x equal 2. So that's the line that we're going to revolve that region around. All right, so as we describe our representative rectangle here, the representative rectangle would go like this now. Okay, from the axis of rotation to our curve. So from our axis of rotation to our curve. So let's see, let's describe big R. All right, now remember, big R is going to be the distance from the axis of rotation to the curve furthest from the axis of rotation. So you're talking about, you look at this, you're talking about big R would be this distance right here. Okay, that's going to be big R. And so big R would be that distance there, which would be, now let's see, now I know this entire distance here is going to be 2. So that whole distance there is going to be 2. From the y-axis to our axis of rotation is 2. And I know that this distance right here, from here to here, is going to be the square root of 1/2 y, I believe, wasn't it? So 1/2 y. So I have to use the y expression, not the x. So it'll be 1/2 y. And that means that this rectangle from here to here would have to be 2 minus square root of 1/2 y. Now, so big R should be 2 minus 1/2 y. Now, little r. Now remember, little r is going to be the distance from your axis of rotation to the bottom of that rectangle. And actually, so the bottom of the rectangle actually touches the line x equal 2. So little r is 0. So little r is 0. So as we set up our integral now, okay, our integral, and like I said, as we look at this problem here, we're revolving this about the line x equal 2, right? So our volume expression be pi. Now we're going to be integrating this time from 0 to 8, not 0 to 2, because we're revolving it about a vertical line, so from 0 to 8. And this would be 2 minus 1/2 y, square root of 1/2 y. So square root of 1/2 y squared dy. And from here, it's just a matter of expanding this. Now to expand this, you have to use the full method to expand it stuff, but simple expansion, and then from there you can substitute your upper bound minus your lower bound in. Okay, so 3 examples. So hopefully you've found some of these helpful. Maybe they'll help you a little bit as far as the washer method, describing your upper bound and your lower bound. Getting big R and little r, so the outside radius and the inside radius. But like I said, the washer method is always a little bit more complicated than just using the disk method. Okay, the disk method, you just have the one radius, that's all, right? But with the washer method, you have two radiuses, 2 radii, if you will. So now if you do this last problem here, if you were to rotate this about this line, we would get some type of a shape like this. So like a horn, I guess. It's kind of hard to draw in 3 dimensions, but that's sort of like it. Okay, I said hopefully you've found this video helpful. Okay, now it's time to go do our homework.